Okay, data transformations. In the analysis of variance procedure, one of the assumptions is that all the populations are normal or really close to normal. And this is not unique to the F-test for the analysis of variance. We saw this assumption throughout previous statistical procedures. Well, what if this assumption is not valid? One remedy to this approach is to transform the data. And some possible transformations might be you take the log of the data, or you take the reciprocal of the data. So you divide the data, each data value into 1, so 1 over x. There's some other transformations that the book gives, and anyway, these can all be done in an effort to try to achieve normality. But note that the normality is now on the transformed data and not the original data. You'll want to read about this, more about it, in your textbook. But what I want to focus on in this video is a non-parametric alternative to the F-test for the analysis of variance setting. And we're going to use what's called a Kruskal-Wallis test. And you might use this if the normality assumption is violated, and then that's needed for the F-test. The Kruskal-Wallis test requires that we have independent random samples, that we have identical continuous distributions of several populations, that they're the same except they may be different by a shift to the left or to the right of each other. All right. The null hypothesis in this situation is that all the distributions are the same, or they're identical, and the alternative is that not all of them are the same. This is our test statistic. Notice it involves NT. It involves, first of all, it involves ranked data. That's what the TI is. What you first have to do is rank all the data irrespective of the samples, and then the TI is the sum of the rank for each sample. And then NT, the other quantity within that sample that we need, of course, is the total sample size, and NI is the individual sample sizes. Okay. It turns out the exact distribution of this quantity is not, there's not a nice closed form representation for it, and so we can use an approximation in that if the sample size is large enough, that we can use a chi-squared approximation here. There are some tables out there online or in various books or other resources that would give you critical values for this particular, the distribution of this H statistic. We're not going to make reference to that in here. We're not going to look those up in any way. Just we're just going to really appeal to the chi-squared approximation. Now, one note here is that if there's many ties, then you may need to use, you will want to use an alternate version of the H statistic, and you'll need to look at your textbook for that. Okay. The rejection region here is we're going to reject if this H statistic is large in some sense. So we reject H naught if H exceeds the critical value of a chi-square distribution for alpha significance level and degrees of freedom equal to k minus 1. Okay, so coming back to the location example, same data. The thing that's a little bit different in the way it presents here is I've got the ranks. I've already ranked the data, and that's what's in the parentheses. Okay, and if there was a tie, notice there were a few ties here, and if we wanted to use the particular representation in the book for this statistic when there's many ties, we can. I'm just going to run through this with the representation as the notes have the H statistic. just to give you a sense of how to work through this particular test. Okay, so here I'm not going to rewrite the parameters of interest. Well, actually, no, I need to. I need to rewrite the in this case, we're looking at the distributions. So I need to rewrite this. So I have several distributions here. Actually, I'm just going to rewrite it in terms of the hypotheses here. So I'm going to, my hypotheses are going to look a little different here than they do under the F-test approach to the analysis of variance. So the null hypothesis here and the alternative hypothesis, the null hypothesis in general is that the K distributions are identical. And so what I would have here is that the, my computer's acting up on me. Here we go. I would have here that the 4 location distributions are the same. And the alternative would be that, well, at least one distribution is different than the others. It doesn't specify which one, it just says that at least one. Okay, so here's our hypotheses. The test statistic is that H test statistic that's above. And so I'm going to go through with the H test statistic here. And so looking at it, it's going to be 12 over NT times NT plus 1, then times the sum of, here I've got TI squared over NI, and this is, and here I is going to go from 1 to 4, plus, or was that minus? Minus 3 times, let me make sure, minus 3 times NT times NT plus 1. Okay. Now, I already know NT is 24. The T1, T2, and T3, I'm going to need those values. Actually, I can get that here, right? T1 is the sum of these ranks, and the sum of these ranks for sample 1, if you add those values up there, you will get 80.5. Okay. You add the ranks together for sample 2, and if you do that, that's called T2, and you get 37. T4, the sum of the ranks there is 103.5, and I'm sorry, that's T3. T4 is 79 there. Okay. All right. So I'm not going to worry about these right here. I've already got the T value. So in my test statistic here, I've got 12 over 24 times 24 plus 1 times the sum. So what I'm going to do is I'm going to take 80.5, square it, divide it by NI. Well, N1 in this case is 6, N2 is 6, and so is N3. Okay. All right. So all the sample sizes are the same. They're 6. I'm going to go to the next term when I equals to 2. Here I've got 37 squared over 6 plus 103.5 squared over 6 plus 79 squared over 6. You go through that computation. I'll let you do that. I get roughly 7.7 with that computation. Okay. Now, that quantity, if we compare that to a chi-squared critical value, I would compare it to, I'm kind of out of space here. Let's see. What would if I'm looking at my rejection region here, I've got a chi-squared distribution, so I'm looking at an upper chi-squared value, and my alpha that I chose here is an upper 10% value. And so if I look that up on the table, I'm going to go to my book real quick. Here, that's back in the F distribution. Chi-squared table here. So here's my chi-squared table, and I'm going to deal with degrees of freedom of 3 because I've got 4 minus 1, and I'm going to look here for 0.90. Actually, no, 0.10 is what I'm looking for, the right tail probability. Degrees of freedom 3, 0.10, I get 6.251 as my critical value there, 6.251. And so my test statistic lies to the right of this, so we would also reject H0 and accept HA here, that at least one of the distributions is different. And this actually coincides with what we saw in the F test. Not surprising. It's fairly typical to get the same results with the F test and the Kruskal-Wallis test, but it's wise to run them both and to, of course, look at your data and your assumptions and see if they're met. But if you run them both and they both agree, then the agreement provides that much more evidence towards what they're saying. Here is the jump output for the test. You can see here the t values, the sums for each, the rank sums for each sample, and here's the chi-squared value that we got in our computation and a resulting p-value. Okay. But anyway, this is the Kruskal-Wallis test. I want you to be aware of it, the ins and outs of it, and the specific distribution of finding exact critical values and exact p-values. I'm not worried about in this class. I just want you to be aware that the Kruskal-Wallis test is a non-parametric alternative for testing the equality of several populations. Okay.